Hello. So for this section, we will be discussing maximum or minimum points of a function. Generically, we can say that these are extreme points or extrema. And we're really talking about the maximum or minimum points of the graph of a function, right? And so you can have a maximum or minimum in several different ways, right? So suppose the graph of a function just looks like this, right? Suppose it sort of tapers off and it goes up and it comes down and then maybe it comes to a corner and then goes up again, but then it levels off, right? So, right, if this is the graph of the function, right up here, this would be your maximum, right? And again, it's a point, although we'll typically be talking about what's called the maximum value, which is just the y-coordinate, right? The y-coordinate of the maximum point, right? So if, let's say, this is your x0 here, or let's call it x1, and then over here you have the y-axis maybe, and then this is y1, so there's x-axis here. Right, so then the maximum value would be y1, and it would occur at x1, right? Likewise, at the bottom here, this would be at x2, and then you would have, well, let's say the point is x2, y2, right? So that would be your minimum point. And the minimum value would be y2. So from now on, I'm just going to abbreviate min for minimum and max for maximum. Right. So these are maximum. Right. This is the maximum value up here, and the minimum value down here. So maximum value is y1, minimum value is y2. Right. So these are also called absolute or global maximum and minimum values. Oops, sorry. Right, yeah, maximum and minimum values, right? Because, right, this up here, this is the highest point for the entire function, right? So the highest point gives you your maximum, and then this down here would be your lowest point, right? So your lowest point gives you your minimum, and your highest point, right, tells you where you have a maximum. Okay. Right. So that's one way to define maximum or minimum, basically the highest point for the entire function or the lowest point for the entire function. Okay. On the other hand, maybe we're not looking at the entire function, right? Maybe we're only looking at a piece of it. So let's suppose instead that the graph might look like this. I can do a little bit better than that. Okay. So again, this presume we have our x-axis and our y-axis over here, right? And then this is just some function. We'll call it f of x as usual, right? So suppose that instead of looking on the entire domain, let's say the domain is all real numbers, that we're only going to look, let's say, from here to here. Right. So only looking on this interval. And let's start the first point as A, the last point is B. So we're going from A to B, right? And let's suppose this is a closed interval, so we do include A and B. So this is a closed interval, which means we include the endpoints A and B. If we decided not to include the endpoints, this would be an open interval. Right? But here we're going to include A and B. Right? So in other words, we go up to the function right here, and then we're only going to consider, let me do this in green here, roughly speaking, this piece of the function. Right, and that's for B, right? So we have this point here, A, say f of A is the y value. This point over here is B, f of B, right? And so now we can still ask the question on this interval, right? So let's call this interval generically, let's just call it I for interval, right? So on this interval, on I, does f have a maximum? What's the highest point on the graph? Right, not for the entire function. In fact, I think we can assume, because this arrow up here keeps going up, right? We assume that the function is going to go up forever. So the function does not have a maximum value in that case. Right, and well, you can say, well, the maximum value is infinity, except remember that infinity is not really a number, right? So when it keeps going up to infinity, we're just going to say it has no maximum at all, right? So we're only considering the green part of the function here, right? So on this green part, do we have a maximum? Sure, right here, right? That's the highest point. This is the highest point for the function. So I would say f of B is the maximum value of the function f, but only talking about the interval I here, right? Not for the entire function, but only on I. So we can also ask, does it have a lowest point? Sure. Right about here, right? So the x-coordinate will be here, and instead of calling it x, let's call it c for now. And so the y-coordinate will be, let's say, f of c. Right? So we can say that f of c is the minimum value of the function, but again, only on the interval I. Okay, so we would still consider this, all right, the absolute, we should say absolute maximum and absolute minimum, right? But only on an interval. Make sense? Okay, so now let's look at another picture here. Let's suppose the function looks like this. Well, okay, let me try again. Okay, and let's say it levels off here, right? So here's the x-axis. Here's the y-axis. Right? And again, we'll just give this name. We'll call it f again, f of x. Right. And so here, we can still talk about absolute maximum. That would be right about here. And then here would be the absolute minimum. So this is the absolute maximum. And since the function levels off everywhere, this is the absolute maximum for all real numbers, right? So on the interval from negative infinity to positive infinity. And then this would be the absolute minimum on that same interval. Right? However, if you look at this point right here, this point on the graph, it is the highest point, not for the entire function, of course, but it's the highest point nearby, right? So it's like the peak of a hill, right? We're not climbing Mount Everest. We're not going way up here, right? But we are standing on top of a hill. And so we can say that this is not an absolute maximum. We can say it's a relative. Let me spell that. Relative maximum, right? And likewise, this point right here, even though it's not the lowest point of the function, it's the lowest point nearby. Relative to points nearby, we can say that this is a relative minimum, right? Right. In fact, some books will call this a local minimum, right? So locally, as long as we don't go too far away, right? If we go far away, we'll have points lower than that, right? Over here. But locally, it is a minimum, right? Likewise, this is a local maximum, even though there are points higher than that, right? If we don't go too far away, if we just look to the left and right, the rest of the function will be lower. So that gives you a relative maximum. Okay. So think of a relative maximum as just a peak, and a relative minimum is a valley. Right? And so for that matter, this point down here, even though it's an absolute minimum, it is also a relative minimum. Relative to points nearby, if we don't go too far away, it's still the lowest point, right? And likewise, if we don't go too far away up here, this is also a relative maximum. So you can be both. You can be an absolute maximum and a relative maximum. Okay. Right. However, let's suppose that we're just looking at a piece of a function, right? Let's suppose we're looking at this piece here. It starts here, right, and it ends here. Okay. So we can identify this point right here, right, as a relative maximum because it is the highest point nearby, even though this point over here is higher. We're only looking nearby, right? This is not an absolute maximum. Likewise, this point right here, this is a relative minimum, but not an absolute minimum, right? So then the question is, what about this point down here? Well, here we could say this is an absolute minimum, but it is not a relative minimum. And the reason is because, remember, you have to look both left and right. Right? If it's the lowest point to the left and to the right, then you can say it's an absolute minimum. But the problem is we can only look to the left, right? We can only look over here because we don't know what happens to the right. I mean, it's just not it's not given, right? Suppose the function were to do this. Well, then we can say it's a relative minimum, right? However, what if the function were to do this? Now, this is not a relative minimum because there are points lower than that nearby. See, so if it's an endpoint, we don't declare this to be a relative minimum or maximum, right? Same thing up here. This up here is your absolute maximum, but not a relative maximum, right? It's not a peak. At least we don't know that unless we know the points to the left of it. So here it would be a peak, which means it would be a relative maximum. But if it went like this, then this is not a peak, and it would not be a relative maximum. So that's the idea, right? So it's just looking at the highest point for the maximum, lowest point for the minimum, and then is it a peak? Oops, yeah, is it a peak for a relative maximum or a valley for a relative minimum? Okay, so that's the idea. Now let's just get to the official definitions. Okay, so we have a function f, right, defined on an interval I that contains c. Okay, so here's a picture of that. So here's the x-axis. Let me use a different color. We have the x-axis, the y-axis, and then we have some function on an interval. Let's say the interval goes from here to here, so from a to b, and it could be open or closed, right? So on this interval, let's say the function looks like this. Then we can say at this point here, let's call it c again, the y-coordinate will be f of c. Right? Oh, I forgot to say that, right, this function is f of x, of course. So f of c then would be the minimum. Oh, I'm sorry. This is for number 2. We'll come back to number 1. Yeah, f of c is the maximum value. I'm just copying down what I have up there, right, of the function f. Right, so the function f on the interval I if, right, f of c is bigger than or equal to f of x for all x on that interval. Right. So what we mean by that is, right, this is f of c up here. Squeeze that in here, right? If I pick any other x between a and b, right, so that x might be right here. I go up, and now I look at the y value, f of x, and I notice that f of x is lower than f of c. In other words, did I get this backwards again? No, that's right. F of x is lower than f of c. That means f of c is bigger than f of x, right? F of c is higher than f of x. So yeah, this is definitely true, right? F of c is bigger than or equal to f of x. But it doesn't matter that I picked this x, right? I can pick this x over here. And I go up, and even though I'm a little bit higher, you can see that my f of x is still lower than f of c. Which means this green point right here, this is the maximum value. All the other points are lower. Make sense? Right, so that's what this definition says. Now let's go back and look at number 1. For number 1, we have the reverse picture. Now we have a function that looks like this. Okay, and again, we're going from a to b, so this is my interval I here. And now we're looking for a c, this c right here, and this is f of c, the y-coordinate. And we can see that if I pick any other x, even very nearby, that f of x is going to be bigger than f of c, right? So we say that f of c is the minimum value of the function f on the interval I if your f of c is going to be lower than or less than all the other f of x's. So you pick any other x on the interval, and you'll see that, yep, it's higher than f of c, right? Makes sense? Even if I picked this x way here, it's going to be slightly higher, just barely higher than f of c, but it will be higher, right? So that tells you you have a minimum value, the lowest point, and the maximum value is the highest point, right? And the interval could be, right, all real numbers, but, you know, here we're just picking a smaller interval just for convenience. Now, not every function, of course, has a maximum or minimum value. I think I have just enough space for that. Suppose, here's my x, here's my y. Suppose I have a function that looks like this. So, yeah, so you can see right here I have some sort of a vertical asymptote. And let's suppose my interval goes from, let's say, a to b here. So I'm only looking at that piece of the function. Let's say this piece here, and then this piece here. And let's say we include the endpoints, although we don't have to. Right? And then this is an arrow going down. This is the arrow going up. Okay. So on this interval, right, from a to b, do we have a maximum? Nope, because it keeps going up, right, forever. And it keeps going down forever. So there's no minimum, there's no maximum, right? And in fact, there's no relative minimum or maximum either. But yeah, so there's no absolute maximum value, there's no absolute minimum value. Just keeps going. Okay. So, right. So that's one way that you might not have a maximum or a minimum. Here's another way. So I'm running out of space, so can I graph over here? So here's x, here's y. And let's suppose that, so here we were including a and b. Let's not include a and b. Let's leave a open, and let's leave b open. Right? In other words, we do not include a and b here. So x is between a and b, but not equal to a and b. So we're not going to put equal signs there, right? So this is what I was referring to earlier as the open interval. Open intervals do not include the left and right sides, the left and right endpoints, right? Okay. So now let's suppose I have a function that looks like this. Again, there's nothing here and nothing here, right? But everywhere in between, for every x in between, of course, there's a y. Okay? So if we're just looking at that piece of the function, again, we'll call it f, do we have a maximum value? Well, if you think that it's right here, that it's f of b, hang on a minute, we're not including b. We can't plug in b into the function. It skips over that point. F of b, right, this point here, f of b is not part of the function. We never make it that far. We can get as close as we want, right? We can plug in an x like right here, right next to b, but you can see that, right, you can't make it all the way to b here. That's the whole point of an open interval. You never get there. You can get as close as you want, but you'll never make it to b. So, right, so you can get as close as you want to f of b here, but you'll never make it to f of b. So there is no maximum. Right? And for that matter, there is no minimum. We never make it to f of a. You can get slightly above that if you pick an x nearby, but that f of x will still be bigger than f of a. And so there's no minimum either. So that's what can go wrong here, right? Okay, so now, what's the condition that guarantees that we do get a maximum and a minimum value? Well, obviously we can't have these open intervals because then there's no guarantee you have a maximum or a minimum. And you can't have these vertical asymptotes, right? Also, you can't have things like broken graphs. Like if I have a graph that looks like this, right? Then there might not be a maximum or minimum on a given interval, right? Well, there is in this case, But suppose it was the reverse. Suppose it went up like this, and then down like that, and then, so yeah, so there might not be a maximum or minimum in those cases, right? In any event, what guarantees that you have a maximum and minimum value is that you have a closed interval, right? One like this that includes A and B, and you can't have these gaps or asymptotes. In other words, it has to be continuous. So let's make that official. Okay, so this is in our book, Theorem 3.1, the extreme value theorem, right? So the extreme value theorem tells us when we have an extreme value. Remember, extreme values are, right, maximum and minimum points, right? So if you have a continuous function on a closed interval, then the function f is guaranteed to have both a maximum and a minimum value on that closed interval. Okay, so yeah, okay, I'm not going to prove this. Again, the proof is in the book. If you're really curious about proofs, you can always send me an email and ask about them. I will prove something. By the end of the semester, we're going to prove a theorem, but not this one. So, right. So then the question is, well, okay, so if we have a continuous function on a closed interval, we know we have a maximum and a minimum. How do we find it, right? So before we can answer that question, we need a few more definitions. Okay, here we go. So, all right, so if there is, all right, so, and this is what we were talking about earlier, so I'm sorry I erased the picture, but if there is an open interval that contains C, on which f of C is a maximum, right, a maximum value, we should say. Well, in the future, if we say f of C is a maximum, we mean maximum value, okay? Then f of C is a relative maximum, right? So a relative maximum just means, as we saw earlier, a peak, right? So if this is your open interval, again, say from A to B, although it's just any open interval, so we don't include the endpoints here, from A to B, right? And your C would be right around in the middle here, right around here. Then this f of C right here, that y-coordinate will be the highest point. So that'll be a relative maximum. Okay, yeah, so again, this is a relative maximum, if I can abbreviate, right? Likewise, you have a minimum, right? A relative minimum if f of C is the lowest point. So those are valleys like this, right? So this point right here would be your relative minimum. Just to abbreviate. Okay, and as I mentioned, they're also called local minimum or local maximum, right? Okay, now, one more definition. We have a function f, right? Let's say f is defined at C, right? Which means C is in the domain of the function. Make sure you're aware of that. If the derivative of the function f at C is equal to 0, or if the derivative fails to exist, then we say C is a critical number for the function, right? And I think be careful here, because in Sal Khan's videos, if you're watching the Khan Academy videos, he calls these critical points, but they're just numbers, right? When you think of a point, you think of an x and a y. And we're only talking about x's here, right? So C is an x coordinate. So I think it's a little sloppy to call it a critical point. And I'm not going to do that. I'm going to call it a critical number. You know, and some people call them critical values, as long as you're aware that we mean critical x values, not y values here, right? Right. So what is a critical number, right? So C is a critical number for a function f, right, if either the derivative of f at C is 0, or if the derivative of f at C does not exist. Okay. So in our picture here, suppose the function does this, right? Then my C would be right here. And so if I take the derivative, remember the derivative is the slope of the tangent line. And so we have a tangent line sitting right here. What would its slope be? Looks like it's horizontal, right? So it looks like the slope is 0, which means the derivative of the function at this point, right, at C, would be 0. That's what makes it a critical number, right? Right? If the derivative of the function is 0, that means it has a horizontal tangent line, right? So a critical number could have a horizontal tangent line. Right. And before you think, oh, well, but isn't that just a relative maximum? It could be. But remember, the graph could also look like this. And in this case, right, this is my C here. I still have a horizontal tangent line at this point, right? So the derivative of the function at C would still be 0. But in this case, it's a relative minimum, not a relative maximum. So if you have a critical number, we don't know necessarily, we don't know that you have a minimum or a maximum. In fact, you might not have either, right? You can imagine a function kind of doing this. Oh, I don't want to do that here. Let's scroll down a little bit. Suppose the function does this. Comes down, levels off, and then it goes back down again. Okay, so right around here, if I draw the tangent line, it is going to be a horizontal line, right? It's still going to have slope 0. So whatever C this is down here, that C will be a critical number because, again, the tangent line is horizontal there. Okay, but it's not a minimum, it's not a maximum. Okay. But you can see there is some relationship here between being a critical number and possibly being a maximum or a minimum. We'll get to that a little bit later. All right, so that's one possibility if the derivative is 0, right? Or what if we have this possibility where the derivative fails to exist? So that might happen when your function looks like this, right? Or like this. Remember absolute value? The absolute value function looks like this, right? So, yeah, so let's say that this is my C here. So what happens at the corner here? Well, there's no tangent line, right? There's no tangent line. So because there's no tangent line, the derivative does not exist, right? At C, at this point here, right? It exists everywhere else, right? You have a well-defined tangent line here and here, but not at C itself, right? And then the same thing goes for up here. Again, because this comes to a corner or a cusp, right? The derivative at that point does not exist. On the other hand, we still want to say that this is a critical number because this is still a maximum and this is still a minimum, right? So, yep, again, a critical number could mean a minimum down here. It could mean a maximum up here, right? Or here. But it doesn't have to. Again, it could look like this over here. Or if the derivative doesn't exist, let's suppose we have a graph that looks like this. It's very steep here, and then all of a sudden it's not so steep. Okay, so this point would not be a minimum or a maximum, but it's still a critical number because the derivative fails to exist there. So you can call this like a joint, right? or a kink in the function. Okay, so it's right. So the c would still be a, let's say this is my c here, still a critical number because the derivative fails to exist, right? So that's the idea of a critical number, and we're going to use these. We're going to use these a lot. So make sure you understand what is a critical number. It's where the derivative is either 0, right, or where the derivative does not exist. It could be either. Right? It can't be both because 0 exists. If the derivative is 0, then you can't say it does not exist. Likewise, if the derivative does not exist, then it can't be 0. So it's one or the other, but not both here. Right? Okay. Okay, so let's get to our first example. We want to find the critical numbers of the function f of x equals x. Well, let me copy it down in case you can't read that, because it is kind of small. 4x cubed plus 15x squared minus 72x plus 18. We want to find the critical numbers. I'll say all critical numbers. Right. Now, it's possible that this function might not have any critical numbers, right? In which case the answer would be, well, none. There are no critical numbers, right? But I think based on the fact that this is a polynomial, in fact, it's a third degree cubic function, it should have critical numbers, and we just have to figure out how do we find them. Right. So remember, what is a critical number? It's where the derivative is either 0 or does not exist. So to find the critical numbers, we need to know what the derivative is. So before we have any hope of finding the critical numbers, let's just take the derivative, right? Right? And not by using the definition, of course, just use the sum rule, power rule, constant times function rule, right? So we get 4 times 3 is 12, times x to the 3 minus 1 is 2, plus 15 times 2 is 30, times x to the 2 minus 1, which is 1. Right? So x to the 1 is just x. Let's not write the 1. And then minus 72 times the derivative of x is 1. Right? And then the derivative of 18 is 0 because it's a constant, so we don't need to write the 0. So there's our derivative, right? So where do we get the critical numbers? Well, either where the derivative is 0 or where the derivative does not exist. So let's look at the possibility, right? Does the derivative, where does it not exist? So notice this is a nice polynomial function, right? The denominator is 1, which is never 0, right? So we're not going to be dividing by 0, which means it has no vertical asymptotes, right? So it is continuous, right? It has no gaps, no jumps, no holes, right? So yeah, no gaps, no jumps, no holes, no asymptotes. This function is continuous, right? In fact, the original function is also continuous, but so is the derivative. Okay, so where does it not exist? Nowhere, right? This exists everywhere, right? The domain is all real numbers. So you plug in any x and you get a y value. Nothing can go wrong here, right? So we're not going to get a critical number because the derivative does not exist. The only other possibility is that the derivative, as we mentioned here, equals 0. So where does the derivative equal 0, right? Or does it? Well, to answer that question, we have to solve the following equation. Right? And you've done these many times before, so you should definitely pause the video and solve this equation any way you want. You can use the quadratic formula. I'm going to do it by factoring, but go ahead and do it. Okay, so I think all of these are divisible, let's see, not by 12, but by 6. So I'm going to factor out a 6, leaving us with 2x squared plus 5x minus, is it 12? Yeah. 6 times 12 is 72, right? So the 6 does not equal 0, right? So we can divide by 6 if you want. I'll leave it there for now. And now we just have to factor the trinomial inside here. And let's see, can we do this very quickly here? If we get 12 minus, no, that's not going to work. How about 8 and 3? So 2 times 4 is 8. 8 minus 3 is 5. So I know I did that fast, but you know, I'm pretty, well, I'm not necessarily good at it. I just happen to get it pretty quickly here. But you know, if you had to use the quadratic formula, right, that's fine too. So if you're not good at factoring, you can always solve these by using the quadratic formula. You could use a equals 12, b equals 30, c equals negative 72, but you're going to get some very big numbers there. Again, the 6 doesn't matter, so I would at least factor out the 6 first. This is the only thing we need to set equal to 0, right? 6 is not equal to 0. So we can divide by 6 on both sides, right? So the 6 doesn't matter here. This still equals 0, right? So yeah, I would use a equals 2, b equals 5, c equals negative 12, and plug those into the quadratic formula, right? And when you do that, you'll get the same thing here. When you set these equal to 0, 2x minus 3 is going to be 0 when x is negative 3 over 2, and x plus 4 is going to be 0 when x is negative 4. So there we are. We have two critical numbers, right? 3 over 2, or if you prefer, 1.5, and negative 4. So two critical numbers, right? Yeah, and you can see they can be any real number. They don't have to be nice whole numbers or integers. They can be fractions or decimals or irrational numbers in some cases. But you know, so two critical numbers, right? These are the critical numbers. Right. And what makes them critical numbers? Well, if I plug these numbers into the derivative, right? Right, don't be careful. Don't plug them into the original function. That'll just give you the y coordinates, and those are going to be important later. But right now we want to plug it into the derivative, and if we do that, we should get 0. In fact, if we don't get 0, then I messed up and I didn't solve this correctly. But I'm pretty sure I did, right? But you can double check by plugging in, say, negative 4 into, again, this function here, the derivative, and you should get 0. And that's what makes them critical numbers. When the derivative is equal to 0, then you get a critical number. So here we get two critical numbers. Make sense? Okay. In fact, I'll do one more example, and you'll see that this is not always this easy. Okay. So we want to find the critical numbers for the function, in this case, g of x. And again, it's pretty small. These exponents are small, so let me copy it down. G of x is going to be x to the power 5 over 3, that's the exponent, minus 4 times x to the power 2 over 3. Okay, we want to find the critical numbers. So before we do that, though, it helps to figure out what's the domain of this function. Right? What are we allowed to plug in here? Right, anything. These are cube roots, right? Cube roots are not like square roots. Remember, you can't take the square root of a negative number. Well, you can, but you get an imaginary number, right? But we don't run into that problem here, right? If you take x to the 2/3, that's just the cube root of x squared. So x could be positive or negative here, and you're not going to get imaginary numbers here. So the domain is all real numbers. Keep that in mind. Now, how do we find the critical numbers? The same way. We need the derivative. Right. So take the derivative, and I hope you got 5 over 3 times x to the 2 over 3, right? 5 over 3 minus 1 is 2 over 3. And then minus 4 times 2/3 times x to the 2/3 minus 1 is negative 1/3. So let's see, we still have 5x to the 2/3 over 3 minus 8 over 3 times x to the positive 1/3. So notice what I did here. We can write this with instead of with exponents, let's go back to radicals. Oh, actually, before we, yeah, okay, now let's do that now, right? So 5 times the cube root of x squared over 3 minus 8 divided by 3 times the cube root of x. Okay, so that's my derivative. And before we go any further, can we get a common denominator out of this? We don't have to, but I think it might be helpful here. So notice that this might as well be our common denominator. So what are we missing here? We're missing the cube root of x. So let me multiply the denominator by the cube root of x. And I have to multiply the numerator by the same thing, right? Obviously, we can cancel them, but we don't want to cancel them. We want to uncancel. We want to get the same denominator here. And if we do that, now the numerator will be 5 times, well, the cube root of what? The cube root of x cubed, which is just x, right? And then minus 8 divided by 3 times the cube root of x. So like I say, we didn't have to do that. But this is very helpful, right? Remember, this is our derivative, right? This is going to be, this is going to be equal to our g prime of x. Got it? Okay, so if that's the derivative, where does it equal 0? Right? Remember, we don't care what the denominator is as long as it's not 0, right? A fraction is 0 when the numerator is 0. So we can multiply both sides by the denominator, and then we just have to solve the equation 5x minus 8 equals 0. And that's not hard. You get x equals 8 over 5, right? I hope. Or 1.6 if you prefer decimals. So that's a critical number, right? Is that the only critical number? Well, that's the only solution to this equation. So it looks like that's the only critical number, right? But hang on. Remember what a critical number is. Go back to the definition. A critical number is a number, C, where the derivative equals 0 or where the derivative does not exist. We didn't look at that here. Where does the derivative not exist? Well, when the denominator is 0. Can the denominator be 0? Well, in this case, sure. We could divide by 3. That doesn't matter, right? Where's the cube root of x equal to 0? Well, when x is 0 cubed, right, which is 0. So we actually get two critical numbers, 8 over 5, or 1.6, but we also get 0. 0 is a critical number, right? Right? If you plug in 0, that makes the denominator 0, and it makes the numerator negative 8, right? So it's not indeterminate. It's just, it's just undefined at 0, right? So, yep. So we get a critical number because the derivative fails to exist. That did not happen in the first example. All the critical numbers came from where the derivative equals 0. But in this example, we actually get a critical number because the derivative fails to exist. Okay? It doesn't happen often, but you got to check that, right? Because if you miss 0 as a critical number, you're going to get it half wrong because that's, only half right. You got half the critical numbers, right? So you'll get half credit for that, right? But yeah, that's going to be important later because 0 being a critical number is going to be a point we want to focus on later, right? Okay. Also notice that it's in the domain, right? 0 is in the domain of the function. You can plug in 0 into g. In fact, let's do it. You just get, right, g of 0 is going to be 0. But this is a point on the graph. 0, 0 is part of the graph. Okay, so yeah, if the derivative is, if the derivative fails to exist, but the original function does not exist either, then it's not a critical number, right? Remember, a critical number, going way back up here, has to be in the domain of the function, the original function, right? It might not be in the domain of the derivative, but it has to be in the domain of the original function. And here 0 is, right? But I'm running out of space. So one last thought here. Let's suppose we have a function h of x is 1 over x. What are the critical numbers? Well, what's the derivative? You better know this by now. You did this on the first test, and you did this the long way. But yeah, the short way is just to do this, right? This is x to the negative 1. Using the power rule, we get negative 1 times x to the negative 2, or negative 1 over x squared, and that should look familiar. That's what you got on the first tests. At least I hope you did. Most of you did, I think. You might have messed up a little bit of the algebra, but obviously when you're using the power rule, that's very hard to make a mistake. At least, I hope you don't. So that's the derivative, right? So where's the derivative equal to 0, right? So we want to solve this equation here. You can multiply both sides by x squared, or let's do negative x squared to get rid of the negative sign, right? So on the left side, everything cancels, and you just get 1, or negative 1 if you made it positive. And 0 times anything is 0. We get 1 is equal to 0, which is not true, right? 1 is not equal to 0. So this equation here, right, this equation has no solution. And then you might think, well, then there's no critical numbers. But hang on. Remember, a critical number is not just where the derivative is 0, it's where the derivative fails to exist. Is there anywhere this does not exist? Of course, 0, right? F prime of 0 is undefined. The derivative does not exist, right? Does not exist at 0. So is 0 a critical number? Critical number? Well, it looks like it because the derivative does not exist at 0. But on the other hand, go back to the original function here on the left. H of x is 1 over x. What if I plug in 0 into the original function? I get 1 over 0, which is undefined. So 0 is not in the domain, right, of the function h. Oh, sorry. Sorry, I switched to h, so this is not f now. I'm really messing that up. This is an h here. This is an h here now. Okay. So yeah, h prime of x, h prime of 0. Right. Anyways, so the point is that it's not in the domain, and so by the definition of a critical number, right, 0 would have to be in the domain, and it's not. So the answer here is no. So here you have to be very careful. Even though the derivative at 0 we'll say does not exist, that doesn't make it a critical number because it has to be in the domain of the original function, and in the original function, it's not in the domain. 0 is, right, h of 0 is undefined. 1 over 0 is not a number. So 0 is not a critical number. So what are the critical numbers of this function? Going back to h of x equals 1 over x. This function has no critical numbers. Right? And I think I mentioned that earlier, that not all functions have critical numbers. This one does not. Okay? But these two did, right? Both example 2 and example 1 had precisely 2 critical numbers. You'll have some functions with only 1 critical number. Other functions might have 2 critical numbers, or 3, or 1,000, or 1,000,000. You can have infinitely many critical numbers, but we're not going to worry about that in most cases. Because that's how to find critical numbers. Very important. Okay, so in addition to finding critical numbers, right, or critical points or critical values, but again, I like to call them critical numbers. We're going to use that idea to do this example. We want to find the absolute maximum and the absolute minimum of the function, and maybe I should write it down again because it's a little small here. So the function is x cubed plus 3x squared minus 24x plus 17, and we want to find the absolute maximum and the absolute minimum. Now, again, there may not be a maximum, an absolute maximum or an absolute minimum. And in fact, if you look at the entire function, there isn't. However, we're only going to be looking on this interval here from -6 to 0. So between -6 and 0, including the endpoints, including 0, including -6. Right? So on that interval, well, this is a continuous function, right? It's a polynomial. All polynomials are continuous, right, on their domains, which is all real numbers. So this is a continuous function on a closed and bounded interval. Remember, it wasn't that too long ago that we did the extreme value theorem, which tells us that when you have a continuous function like this, right, this is continuous, right, and it's on a closed interval, it includes the endpoints, 0 and -6, right, then that guarantees you have an absolute maximum and absolute minimum. Okay, so now we just have to find them. Right, so how do we find the absolute maximum or minimum of a continuous function on a closed and bounded interval? And in fact, even if the function is not continuous or it's not on a closed interval, it still might have a maximum or minimum. So, right, so even if the extreme value theorem doesn't apply, you can still use this procedure up here to help you find the absolute maximum or minimum. Just be aware that there might not be one. There's no guarantee that there is one. Right? So this is the procedure up here, right? So this step-by-step process here that we're going to use to find the absolute maximum or a minimum on a closed interval. Let's say it's from A to B, right? Okay, so step one. So step one, find all critical numbers on the open interval from A to B, right? So we need to find all critical numbers, if there are any, right? There might not be any. Critical numbers of this function from -6 to 0, and we're not going to include -6 and 0 here, although you can, but it's redundant to do that. So the endpoints could very well be critical numbers, but we're going to exclude that possibility here. Okay, so how do we find critical numbers? Usual way, take the derivative. It's an x minus 24, right? So 3x squared plus 6x minus 24. Now, right, because it's easy to forget, don't forget that a critical number is where the derivative is either 0 or does not exist. Well, this derivative here will exist everywhere. And if it exists everywhere, the only critical numbers would come from where this equals 0. So now, when we set this equal to 0, what do we get? So it's another quadratic equation. Again, if you're more comfortable using the quadratic formula, go right ahead. In most cases, you won't need it because you can factor it pretty easily here. Again, the 3 doesn't matter. Yep, I think we get x equals 2 and x equals 4. Right, 3 is not a critical number, right? It's not x equals 3. You can divide by 3 on both sides. Right, so the 3 is just a coefficient. Right, so we get two critical numbers, 2 and 4. Now, the first thing we have to check, of course, hang on. That's wrong. What did I do wrong here? Well, it's easy to make a mistake, isn't it? So this is right. If you check this, you get x squared minus 6x plus 8. So I have the wrong sign here, and I have the wrong coefficient here. So yes, this is wrong here. What's wrong is one of the signs, right? They have to multiply to negative 8 and add to positive 2. Negative 2 plus negative 4 is negative 6. So I think what I want here is a plus sign in front of the 4. 4 minus 2 is 2, and negative 2 times positive 4 is negative 8. So in other words, yeah, so when you solve this here, x is going to be equal to negative 4. So the two critical numbers here are 2 and negative 4, not positive 4, right? Okay, so two critical numbers. But remember, we only care about the critical numbers that are between negative 6 and 0. So negative 4 is certainly between negative 6 and 0. So we want that critical number. But 2 is bigger than 0, right? So negative 6 is less than 0, but 2 is bigger than 0, so 2 is not between negative 6 and 0. So even though it's a critical number, it's not a critical number on this interval between negative 6 and 0. Okay, so we're going to ignore that, right? At least for step 2, we're going to ignore that, right? So what do we do in step 2? For each critical number, plug it into the original function, right? So here's the original function. So just evaluate this at, right, not 2, of course, because that's bigger than 0. It's not on the interval. But negative 4, we can plug that in. And what do we get? We get negative 4 cubed. You can just use your calculator, but let's write it out by hand, maybe once and never again. So you plug this in your calculator, and I think you get 97. But I better double check that. Yep, I think you get 97, right? All right, but that's all there is to do in step 2. Plug in the numbers in the original function. Yeah, be careful you don't plug them into the derivative. If you do that, you'll just get 0. Right? In fact, that's what makes it, that's the definition of a critical number. So if you're always getting 0 here, be careful. We don't want 0. We want the y-coordinate. We want 97, right? We don't want the slope of the tangent line. We just want the coordinate, the y-coordinate, right? So, yeah, this will occur at a point. Negative 4 is the x-coordinate. 97 is the y-coordinate. Okay. Step 3, evaluate f of a and f of b. Okay, so what's a and b? Well, a is the negative 6, and the b is 0 here, right? We're going from a to b, so from negative 6 to 0. So in step 3, we just have to plug in two more numbers, the negative 6 and the 0. The 0 should be easy because that's just 17. And the negative 6, I'm not going to write it out, but you get 53. Plug it in your calculator. You should get 53. Okay. So that's step 3. You're just plugging in the a and the b. Oh, and if there were no critical numbers, then there's nothing to do in step 2. If there's no critical numbers, or maybe there's a critical number, but it's, let's say, less than negative 6 or bigger than 0, then you don't do anything in step 2. You don't get any numbers there. You just skip to step 3. Okay, but here we did get one critical number, the negative 4, between a and b, and we plugged that in and we got the 97. So we're almost done. In step 4, all we have to do is look at these three numbers that we got in step 2 and 3. We got three numbers. We got 97, 53, and 17. Okay. So in step 4, what do? Find the smallest and biggest. So the largest number out of these three numbers, and it might help to write them in order, right? 17, 53, 97. We want to find the biggest and the smallest number. Well, the biggest number is 97. So that's your, That's your absolute maximum value, right? That's the highest point, the highest value of the function. And then the smallest number, the 17, that's your absolute minimum, right? Or minimum value. That's the lowest point of the function. The 53 is neither, so we can dispense with the 53. So we get an absolute maximum. So to answer the question, we get an absolute maximum of 97, and it occurs at x equals -4. So, right, if the question is to find the maximum point, and again, it should be clear from the question, here it just said find the maximum and minimum, so the maximum is 97. The maximum point would be -4, 97. Right, so there you're looking for both the x and the y. But the maximum is just the maximum value, in which case, and that's just 97, right? And then we have an absolute minimum, again, abbreviate, of 17, 17, and that occurs at x equals 0. So your minimum point is, 0, 17. Right. So this answers the question. You have an absolute maximum of 97 and a minimum of 17. And these are the points at which they occur. Okay. Now, of course, the other way to do this problem is just to graph the function and, again, cut it off at -6 and 0 and look at that piece of it, look at that piece of this function on the graph, and then just figure out what's the highest point and what's the lowest point. You know, that's a crude way of doing it, but you can do it that way, and maybe on your calculator if it helps. But this is the way to do it algebraically, and this is the way we want you to do it in the homework and on the tests. You know, if you want to use your calculator to check your answer, that might be helpful. But if you just write down the answer and you don't show any of this work here, don't expect to get credit for that, right? You know, it's good that you know how to graph it. It's good that you know how to do it other ways. But this is the, you know, formal algebraic way to do it. Okay. Yep, we'll do another one because this, again, this takes some practice here. Okay. Example 4. So this is, again, we want to find the absolute maximum and minimum of the function f of x equals, so let's write it down here, f of x. So this is a rational function, 2x over x squared plus 1. On the closed and bounded interval from -2 to 3. Okay. So first of all, what's the domain of this function? Well, if you notice, if you take the denominator and set it equal to 0, this has no real solution. Right? You do get imaginary numbers. You get, right, x equals plus or minus I. But those are not real numbers. They're not, I mean, you can't graph those, so we're just going to ignore those. So the domain here is all real numbers. Right? Just to mention that. All right, so now how do we find the absolute maximum or minimum? Well, we're going to do the same thing we did here. Right? First step is to find the critical numbers. So how do you find the critical numbers? Usual way, take the derivative and set it equal to 0. Now, to do the derivative properly here, we need the quotient rule. So low d high minus high d low. And the derivative of the denominator is 2x also, right? Over the square of what's below. So x squared plus 1 squared, right? And we can simplify this a little bit. We're going to get 2x squared plus 2 minus 4x squared all over the same denominator. Let's not multiply that out. But we get like terms here, so we can 2x squared minus 4x squared is negative 2x squared plus 2. Right. And in fact, we can go even further. We can factor out a negative 2, and then we just get x squared minus 1, the same denominator squared. In fact, we can factor this as the difference of squares. This is just x minus 1 times x plus 1, or vice versa, over x squared plus 1. Again, don't forget to square it, right? So all that simplifying, remember, and we want to set this equal to 0. Again, just the numerator. And what do we get? We get x equals 1 and x equals negative 1. So two critical numbers. Right. Now, does the derivative not exist somewhere? No, right? The derivative, the denominator is never 0. Right? Remember, that was the first thing we did, set it equal to 0, and we didn't get anything. Or we didn't get real numbers, right? So the denominator will never be 0. Right? So this will exist for all real numbers, right? Okay. Now, be careful, right? We got two critical numbers, negative 1 and 1. Oh, I should have reversed it. Negative 1 and positive 1 in that order. But are they on this interval? Are they between negative 2 and 3? So here's negative 2, negative 1, 0, 1, 2, 3. Of course, yeah, negative 1 and positive 1 are both between negative 2 and 3. So here we got to look at both of them, not just one, right? Not just negative 1, not just 1. So we're looking at both critical numbers in step 2. Okay, so what's step 2? It's to plug in both of these numbers, all the critical numbers, plug them in to not the derivative, but the original function, right? This function up here, right? Because if you plug them into the derivative, what are you going to get? You're going to get 0. That's why they're critical numbers, because the derivative equals 0, right? I mean, let me just remind you of that. If I take f prime of negative 1, you get 0. If I take f prime of positive 1, you get 0. But that's not what we're looking for. We're looking for the y coordinates, right? So when you plug these into the original function, what do you get? You get, well, 2 times 1 divided by 2. So you just get 1. And if you plug in 1, you get, again, 2 over 2. You get 1. So you happen to get the same number for both. They're both equal to 1. But that's okay, right? So that's right? This will be a possible maximum or minimum. And then what was step 3? Step 3 was to plug in the a and the b. In this case, a is negative 2, and b is positive 3. So we plug those, again, into the original function. Don't plug them into the derivative. So here, what are we going to get? We're going to get, let's see, negative 4 over 5, or if you prefer, negative 0.8. And when you plug in 3, you're going to get 6 over 10, which is 3 over 5, which is positive 0.6. Okay. Again, I did that very quickly. I think I'm right, but you might want to double check. Right. And now we're on step 4. The last step is to look at all the numbers from steps 2 and 3. So we actually have 4 numbers, right? Well, hang on. We have 3 numbers, right? 1 is the same for both here, right? So we don't want to count it twice, right? Yeah, we get 3 distinct numbers. The numbers are negative 0.8, 0.6, and 1. So, right, the biggest number is 1, right? It's bigger than 3/5. So this is the absolute maximum value. And then the smallest number has got to be the negative 0.8, and that will be the absolute minimum value of the function. And that's what we were looking for, right? It didn't say maximum or minimum points. However, since we can find their y values pretty quickly here, or we did that already actually, right? The absolute minimum point is an x and a y, so negative 4/5. Oh, sorry, that's the y value. I'm sorry. The x-coordinate is negative 2. The y-coordinate is negative 4/5. And then the absolute maximum is going to be, well, it occurs at two different places. It occurs at -1 and +1. So, right, that can happen. You can have your maximum value occur at more than one point. Right. Right. Just think of like the sine function. It goes up and down, right, like this. So your maximum value is 1, but it occurs at all these x-coordinates. It occurs at this x, C1, C2, C3, and they just go on forever, right? So there are actually infinitely many critical numbers, but there's only one maximum value. Right? For the sine function, sine of x, right? The maximum value is 1. That's the highest point. And the minimum value would be -1. Right? So yeah, it can occur at more than one point, and that's what happens here. Okay. I think that's probably good enough. Yeah. I think that'll do it for this video here. So again, most of the problems you're going to do in the homework are finding the absolute maximum and minimum values of a given function on a closed interval. And again, not all of them will be continuous, but even if a function is not continuous, it might be continuous on the given interval. Right? So for example, if your function, just to go back to, oops, I want that color. Okay, I guess I'm not going to end it here. I just want to mention one more thing. Remember 1 over x, this is not continuous at 0, right? But it is continuous everywhere else. So if they give you an interval, let's say from 3 to 7, well, that does not include 0. 0 is less than 3. So this function, even though it's not continuous at 0, it's continuous from 3 to 7. Right? And then you can find the maximum and minimum values there. In fact, we can do it very quickly. We get 1/3 and 1 over 7. So 1/3 is the maximum value, that's the biggest number, and 1/7 is the minimum value. That's the smallest number. Now, you're thinking, well, didn't I skip a whole bunch of steps? What about the critical? Don't we have to find the critical numbers and then plug in the critical numbers? Well, if you remember, we took the derivative, and it's never equal to 0. And in fact, it's undefined at 0, which is, again, 0 is not a critical number here. But it's never 0, so this has no critical numbers. I think we mentioned that already. Oops, no critical numbers. So if it has no critical numbers, then your step 2, there's nothing to plug in. There is no c. So I went directly to step 3. I plugged in the a and the b into the original function, and well, that's right. So 1/3 is the biggest number, 1/7 is the smallest number. So, this went very quick to find again, we're finding the absolute maximum and minimum of this function on this interval here. So even though the function is not continuous at 0, it is continuous on this closed and bounded interval, and so it will have an absolute maximum and minimum on that closed interval. So that was a quick one, but for most of the other problems, you just have to make sure that when you find the critical numbers, make sure you examine where the function, where the derivative does not exist. That didn't happen in this example. It didn't happen in this example. And it did happen in this example, but so the derivative fails to exist at 0, does not exist, but it doesn't make it a critical number because, well, the original function is also not equal to 0. So it is an important distinction here, but at x equals 0, we do have a vertical asymptote, and that does become an important point going forward. Not a point on the graph, but an important matter when dealing with finding maximums and minimums here. So little technical detail there, but for the most part, if you just follow this procedure here, these 4 steps here, right? These 4 steps here. Sorry, I'm crossing it out. I'm sloppy here. If you follow these 4 steps, that should find you the maximum and minimum. In this case, just absolute maximum and minimum of a function. Oh, how do you find the relative minimum and maximum? We'll do that in section 3.3, I believe. So that won't even be on the second test. That'll be on the third test. But finding the absolute maximum and minimum, that will be on test 2. That will be on the next test. So make sure you understand these 2 examples very clearly.